All right, so kth element of two sorted arrays. So they give us array 1 and array 2. These are both sorted, and they want the fifth element in the amongst these two arrays that are sorted. So for example, if we put those two arrays together and we had some final sorted array, the fifth element would be 1, 2, 3, 4, and 5. So this would be the fifth element here, which would be 6. So we return 6. Okay, so let's talk about how we're going to do this. So what we're going to do is we're going to partition our arrays in a way where we find the k smallest elements. And once we have our k smallest elements, we can just return the kth element. So for example, let's pretend that I partition let's pretend I have two arrays here. So this is one array and this is my larger array. And I want to partition this first array. Let's say I take one element from here. That means, and if k equals 5, I have to take 4 elements from the other array. It's because this would give me 5 elements. And what I'm claiming here is that these are my 5 smallest elements amongst these two arrays. And now we need to actually check, are these my 5 smallest elements? Because if they're not, then we have the wrong partitioning. And we're going to keep looking for it. We're going to correct our partitioning until we get the correct one. So well, we got to ask, okay, well, is everything inside a partition smaller than everything outside the partition? Because if there's something smaller that is outside the partition, that means we have the wrong partition. We don't have the k smallest elements. So is this 1 less than this 3? Well, it'll always be, so everything on the left within the same array, everything on the left is always going to be less than everything on the right, because this is a sorted array, right? So everything here will always be less than everything on the right because this is sorted. But what we need to check is across the two arrays. So what we need to do is like check, is this 1 less than this 12 here? Yes, it is. But this 9 is greater than this 3, which means we don't have the smallest elements in our partition. In this case, we don't have the 5 smallest elements in our partition because we found something outside the partition that is actually smaller than what we have inside the partition. So what we're going to do is we need to get rid of this 9. So let's just say I decrease this partition by 1. If I decrease this partition by 1, that means I have to increase the other partition by 1, right? Because we want 5 elements here. So now we ask ourselves the same question. Do we have the 5 smallest elements? Well, is this 3 less than this 9? It is. Is this 8 less than this 5? No. Which means we found something outside our partition that is smaller than what's inside the partition. So we don't have the 5 smallest elements or the k smallest elements in our partition. So we're going to decrease this partition by 1 and increase this partition by 1. And now is this 5 less than this 8? It is. Is this 4 less than this 7? It trying to have the 7? Yeah, so 4 is less than 7. So yeah, when we check like in an X, like when we check if it's less than or equal, then we confirm that we have the 5 smallest elements or the k smallest elements, because everything inside the partition is less than or equal to everything outside the partition. Okay, and once you have the correct partitioning, so we just essentially found the 5 smallest elements or the k smallest elements. So once we did that, all we got to do is look at the greatest number in these two partitions. So it's either got to be this number or this number. And because, again, this is sorted and the greatest number must be the one furthest to the right in both these partitions. And we need to take the maximum of the two. So in this case, we compare the 5 to the 4. The 5 is bigger. So that must mean that 5, if we have the 5 smallest elements, and that is our biggest number in those 5 smallest elements, that must mean that 5 is our kth element that we're looking for. So give me a second. Okay, so let's talk about how we're actually going to efficiently find the correct partitioning. So what we're going to do is we're going to binary search for the correct partitioning. So the way I did it right now is I did it linearly, but we're going to binary search for it. So I'm just going to get into the code, because I feel like if I don't want to overload you guys with like all this information. And I think it's better if I just like walk through the code and just do examples for every line that's not immediately obvious. So what we're going to do is let's comment this out. I'm going to leave this here in case I need it again. Let's try to guarantee, I want to guarantee that array 2 is my biggest array, because that'll make the logic easier. So what I'm going to check is if array 1 is bigger than array 2, then let's just swap the parameters. So I'm just going to call kth element again, but I'm going to flip the arguments. Okay. So we're not actually going to use array2.length and array1.length. They originally these were like m and n, but that's so confusing when you're like actually typing out code. So I just did away with them. But anyway, we are going to use array2 and array1. Okay, and this k here. Just wanted to make that clear. So all I did was if array1 is bigger than array2, then swap array2 and array1 within the parameters. Okay. So now let's talk about the range of our binary search because it requires a little bit of thought. So let's start with our low in our binary search. We have a low, we have a high, and then we have a midpoint in a binary search. So for our low, this is going to be. I have to use an example for this. Let's say so I have 10 elements here. You can count them. You can pause the video and count them if you want, but there are 10 elements here. You can take my word for it. There's 10 elements there, and there's some elements in there. I don't care what that number is, but let's say there's 10 here, right? There's 10 here. Let's say k, in this case, is equal to 12. If k is 12, notice that 12, this k here, is bigger than the number of elements I have here. So what that means is we need at least 2 elements from the smaller array. So for example, let's say, I'm going to let me kind of soft prove why. So let's say I partition the first array like this, where I take nothing out of the first array. If I take nothing from the first array, well, that means I have to take as much as I can from the other array. So I'd have to partition it like this. But if we look at our partition here, we only have 10 elements, but we want 12. So what we actually need to do is we need at least 2 elements from this other array. So what we're going to do is say low equals math.max of array2.length, because array2 is our bigger array, and we're going to do k minus that. And let's say k is smaller than array2.length. We're going to set this to 0. And we actually want this, so low is going to be an index, so like inclusive. So if 12, say this is 12 and this is 10, 12 minus 10 is 2, but that would mean that we want it to be at index 1, because right, we'd have index 0 and index 1, that would be 2 elements. So what we're going to do is we're going to subtract 1 here, because this would give us index 1, right? 12 minus 10 is 2, 2 minus 1 gives us index 1. Okay, cool. So, and if this is some negative number, then we just set it to 0, index 0, okay? And for the high, this was going to be, okay, this is actually a really easy one. So let's say k here, let's say k is 2, right? If I just want the second smallest element, or the second element between these two sorted arrays, well, if I know this is my smallest array, right? Well, if k is 2, I can only take at most 2 elements from this. I can't partition it like this, because this would be 4 elements here, right? And k is only 2. So k can be at most 2 here. And then if I say I took 2 elements from this first array, well, that would just mean that I partition this first array like this, where I take nothing from this one and I take 2 from this one. So yeah, so what we're going to say is I equals the math.min of k and the length of the array. So for example, if k is bigger than the array length, then we just want the array length as our upper bound for our binary search. Okay, so I think that covers our low and high pretty well. So now we're going to just binary search. Almost done, guys. So while low is less than high, what do we need to do? We need our midpoint, right? I'm gonna call this, let's see, what should I call this? I'll call this partition index. So this is my midpoint in this thing. Now, this is a hard variable name to actually come up with, but let's stick with mid, whatever. So low plus, and I'm gonna explain what this mid represents with an example in a second. So we're gonna do low plus high minus low divided by 2, in case there's integer overflow, because why not? So this is our midpoint. And now what does this midpoint actually represent? So let's just copy paste this down here. let's pretend that this is my low, so L for low, and let's pretend that this is my high out here. This is so high is exclusive, right? That's why I put it outside the array, and low is inclusive, and let's just say it's 0. So our mid, so let's just, how many elements do we have here? We have 1, 2, 3, 4, 5, 6, 7. So 7 divided by 2 is, what is that, 3? Yeah, so that would be 3 in integer division. So that would be index 3. So 0, 1, 2, 3. So our midpoint is going to be here. Okay? What this represents is the last index in our partition. So whatever our midpoint is, you could think of like the bar that separates our array as being like in between. So this is just midpoint is just the last, it's just the index of the last element in the partition that we're choosing. Okay? And let's say that let's just say I had one, what's a good way to do this? Let's go with a 4 here. And then we'll just put a bunch of extra numbers, okay? Okay, so I just want to show you what the binary search is going to look like. So let's say this is my bigger array here, and this is my smaller array. And this is how we're starting out, right? Where I choose 4 elements from here. And let's just say that k in this case equals 6. So if I chose 4 elements here, that means I'm going to partition the other array like this, to where I take 2 elements from here. And then I'm going to ask myself, is this 7 less than this 5? And I'm going to ask myself, is this 4 less than this 20? So I need these 4 values here so that I can compare them, which means I actually need this index here, right? So I need, so how do I get this index? This is just going to be, this is dependent on k, right? So let's just call this mid2. So if we call this guy m2, mid2, whatever, this is going to be equal to k minus mid. So let's just, so in this case, k is 6. So if k is 6 minus our midpoint, which this would be, let's see, 0, 1, 2, 3. This would be index 3. So this gives us 3 here, but what we want is index 1 here, because this is index 0, this is index 1, right? If I put this, if I actually write out indexes, if k is 6, and this guy right here is index 3, I'm going to put some numbers just to be really clear. So 6 minus 3 is 3. So we actually need to decrement by 2 here to get us that index 1 for the midpoint, for that other midpoint in the other array. So I know it looks kind of gross in the example, but if you just work through it on your own and you do a little bit of quick math, you'll see that you have to subtract 2 here to get the correct index. Okay. So now what we're going to do is, let me get rid of this because this is in the way. So we need to get those 4 values, right? Like, so that we can compare them. So let's just call this L1. So you know what? Let me, I don't want to confuse you guys with my variable names, so I'm going to really quickly explain what they are before I even type them. So let's just say I have this partition and I have this partition. This is going to be my L1 value. This is going to be L2. And I'm just calling L for left. So like the left in array 1. So this is going to be this 5. L2 will be this 8. And we'll just call this R1 and R2 here. So for this 7 and this 9. Okay? I'll leave that there for a second. So anyway, L1 is just going to be R1 of the midpoint, right? Because we said that this was M. And L2 just going to be R2 of mid 2. Okay, cool. So now, and then what we actually need to do is this mid 2 here, this could technically be like -1, because what if we took say we took everything from the first array and we take nothing from the second array. We need to make sure that this mid 2 is in bounds. So if mid 2 is greater or equal to 0, okay, then we're good. But if it's less than 0, we're going to set this to, we want to set it to a value that will just make the comparison valid. Or it'll make the comparison, it'll make it valid. So we're going to say integer dot min value, because this is the left, and when we compare this left to the right, we're just going to check if the min value is smaller than whatever's on the right, and this will just be true. Okay. So now let's do R1 equals array 1. This is going to be, so R1 is just going to be one index past, or it'll just be m plus 1, right? Because this is index m, and that L1 is this value here. So we just want m plus 1 for this index here, or for R, to get the value of R1. So let's do that, m plus 1. But it could be out of bounds. So we got to check if m plus 1 is less than array1.length, then this is going to be okay. But if it's out of bounds, we're just going to set R1 to some value that makes the comparison valid. So we're going to do integer dot max value. Okay. And now we just need to do R2. So R2, this is going to be 1, or our mid, oh, did I do m plus 1? This should be mid plus 1. And this should be mid plus 1 as well. Okay, sorry. So R2, this should just be mid 2 plus 1, right? And we're going to do the same thing. If mid 2 plus 1 is less than R2.length, then we can go ahead and grab it. So mid 2 plus 1. And we do the same thing where we just set to the max value. All right, so now that we have our 4 values, we just need to compare them. So I'm gonna go ahead and leave this here just so you just have something to refer to. So we're gonna check if L1 is less than or equal to R2 and L2 is less than or equal to R1, then we can go ahead and return R1, or we can go ahead and return the maximum, because remember, so like now that this means that we found our correct partitioning, basically, because whatever's on the left of our partition is less than or equal to something on the right, to the other array's right partition, and everything in the left of the second array in the left partition, everything in the second array's left partition is less than or equal to the first array's right partition. So we found a valid partition. So now we need to return the maximum of these two numbers here. So we're going to do math.max of L1 and L2. Okay. Now if let's say that L1 is greater than R2. So if L1 is greater than R2, this means that we need to, so that means we need to decrease the partition for L1. So we're going to say high equals mid, because we need to, if the left half has some number that is greater than, if the first array has a number that's greater, then we need to decrease that partition in that smaller array. So we're going to say high equals mid, and otherwise this means that L2 is greater than R1, which means we actually need to decrease decrease the partition of the bigger array and increase the partition of our smaller array. So we're going to say low equals mid plus 1. Okay, and I think we're good. That will handle the binary search. So now we have one line of code left. So let's say that low ends up equaling high. If low equals high at some point, we get out of this loop without ever finding a valid partition. What that means, because this low, remember, this mid represents the index. So let me just copy an example here. So remember that this, if say we partition this first array like this, and this mid here, this represents the index the of our of the last thing in our left partition. But in the case where we don't take anything from this array, so for example, let's say that we had an array of like all nines. Actually, let's just leave it like that. And then we had some other, and then our other array, our bigger array, let's say it had all ones. Then, and let's just say that k equals, I don't know, 2 or something. Well, we'd end up, the correct partition would be this. So m, our midpoint, will end up equaling, say, -1, because we're never going to take something out of this. So in that case, we're going to return R2 of k minus 1. Whoa, okay. My computer just like bugged out. Okay, I'm just going to finish this. Yeah, this would be k minus 1, because we're just, basically if we never find a valid index here, so in case if we never find a valid midpoint, then that means that we just have to take everything from our bigger array. And because k is 1 base, we just subtract 1. So we do return array 2 k minus 1. Okay, now I'm going to run this, take out, I don't know why my computer's doing that. Super sorry, I don't know what I hit. I'm going to run it and see what happens. All right, so I got the right output. Let's submit it. Holy cow, I've coded it right on the first try. All right. Well, I've coded this before, but I didn't think, it's kind of hard to code this correctly the first, like, anyway. Yeah, so the time complexity of this ends up being big O of the minimum, or sorry, big O of the log of the minimum of array 1 or array 2. So let me just type it out so you guys can see it. So time is going to be big O of log of the minimum of array 1.length and array 2.length. I'm going to fix my computer after this. Because we're only binary search. So we do the minimum here because we're binary searching on the smaller array, which will just be one of these two, right? So yeah, that's the time complexity. And then space. Space is just O of 1. Yeah, because we don't use any extra space, so it's O of 1. All right. Sorry if that, guys, so that was rough. I don't know why my computer bugged out at the very end there. But yeah, hopefully this helps. You give it a thumbs up if you want. And you can subscribe. Cool. Bye.